Hey everyone, welcome back to The Explainer. Okay, we have a ton of incredible material to get through today, so let's dive right in. I want to give a huge, enthusiastic welcome to all the statistics majors joining us. Today, we're tackling a massive, literally absolutely crucial topic from Chapter 9 of our survey sampling material, and that's how to estimate variance for nonlinear estimators. Now, if you've been feeling pretty comfortable calculating variance for simple means and totals, well, buckle up, because today we are learning how to handle the tricky, messy, real-world parameters. It's going to be fun.
To ground our discussion, we're pulling this directly from the brilliant curriculum of the University of New Mexico's STAT 472 and 572 sampling course. Now, I know you all already have a really solid foundational knowledge of calculus, simple random sampling, and basic variance. We're going to lean heavily on those mathematical muscles today as we make the leap from simple linear combinations into much more complex survey designs.
Here is our game plan for the explainer. We'll hit 1. Variance in complex surveys. 2. Linearization and Taylor series. 3. Replicating the survey design. 4. Dividing into random groups. And finally, 5. Evaluating estimation methods. Let's get to it. Section 1. Variance in complex surveys, the non-linear challenge. Let's take a second to actually set up the theoretical problem we are trying to solve here. Like, why do we even need a whole new chapter for this? Well, the crux of the issue is this. Mostly, the previous chapters you've studied covered variance for linear combinations of means and totals. That's great, but in the real world, our parameter of interest, which we call theta, is very often a nonlinear, smooth function of those population totals. Think about things like ratios, correlation coefficients, or complex economic indices. We represent this mathematically as theta equals a function, h, of population totals T1 through Tk. And here's the catch. Because h is nonlinear, we literally cannot just pass the variance operator straight through it like we do with linear equations. It doesn't work. We need entirely new tools to handle this kind of complexity. Section 2, Linearization and Taylor series, the calculus approach. This brings us right to our very first major tool for solving this problem, and it involves using the Taylor series to mathematically flatten out our complex functions. So let's roll up our sleeves and walk through the algebra of linearizing a ratio estimator, which we represent by a capital B. Remember, B is just the total of y divided by the total of x. To use our familiar linear variance rules, we have to flatten this curve. Okay, step 1, we take the partial derivatives of our function with respect to both variables. Taking the partial with respect to x gives us negative y over x squared. Then, step 2, we apply a first-order Taylor expansion around the true population totals. And honestly, this is the brilliant part. It takes this messy, nonlinear curve and simplifies it into neat, actionable linear pieces. By step 3, we substitute in those partial derivatives, do a little algebraic manipulation, and define a completely new artificial variable, zi. We set zi equal to yi minus b times xi. What we've just done is transform the variance of a complicated ratio into the variance of a simple total of z. Now, I want to slow down for a second because the final result of all that messy calculus is actually quite beautiful. The linearization variance for the ratio estimator, v sub L of b, is approximately equal to the finite population correction, which is that 1 minus n over n part, multiplied by the sample variance of the residuals, s sub b squared. Then you divide that whole thing by the sample size n times the sample mean of x squared. If you're thinking back to Chapter 4 on simple random sampling right now, this formula should look incredibly familiar. By linearizing the estimator, we've essentially wrestled a complex, nonlinear ratio right back into a standard SRS framework, where we just evaluate the variance of the residuals. It's like a statistical magic trick. Section 3, Replicating the survey design, the resampling approach. Now, what if you are sitting there thinking, I really don't want to deal with partial derivatives? Well, good news. Let's pivot from the calculus-based linearization method to our second major methodology, which is random groups and resampling. We've got two distinct flavors of this approach. In the first one, replicating the survey design, you physically draw a sample, record your data, replace the units back into the population, and draw again. You do this completely independently r times. Contrast that with the second method, dividing the sample. Here, you draw your massive, complete sample just once. Then, you take that single sample and partition it into r pseudo-independent groups. These groups act as miniature versions of your total survey. But no matter which flavor you use, the goal is exactly the same, to create multiple estimates so we can measure the variance between them. Let's ground all this resampling theory in some actual real-world data from example 9.3. Say we want to estimate the ratio of out-of-state tuition to in-state tuition. Instead of doing any calculus, we pull 5 independent simple random samples of 10 colleges each. Notice how for replicate 1, the ratio estimator is 2.425, but if you drop down to replicate 4, it falls to 2.051. Because we made 5 independent draws, we're naturally going to get slightly varying tuition ratios. And here is the secret sauce. The variability between these 5 different estimates is exactly what gives us our variance.
So we calculate our parameter estimate, which we'll call theta tilde, simply by taking the average of those 5 replicate estimates. That gives us 2.246. Then, to get the standard error, we just calculate the sample standard deviation of those 5 numbers and divide by the square root of 5. Boom! We have a concrete standard error of 0.0784. From there, putting together a 95% confidence interval is an absolute breeze. We use a t-critical value of 2.78 for 4 degrees of freedom, and we establish that our confidence interval for the tuition ratio is between 2.03 and 2.46. Look at that. We successfully estimated variance for complex ratio, and we didn't have to take a single derivative.
Section 4, dividing into random groups, miniature surveys. Now let's see how this builds into practical, everyday application. Because let's be real, replicating a full, massive survey 5 separate times is usually way too expensive in the real world. So in practice, we usually do the second flavor, dividing a single complex survey into pseudo-independent random groups. But how do we technically divide up different types of sample structures? Well, the golden rule you must always remember is that each miniature group has to mirror the original sample design perfectly. For a simple random sample, it's easy. You just randomly divide your total n observations into r equal groups. For a cluster sample, you randomly divide the primary sampling units, or PSUs. The underlying observation units literally just follow their PSU into whichever group it gets assigned to. But for a stratified multi-stage sample, it gets a lot trickier. You actually have to sample PSUs from every single stratum into your random groups. This creates a really strict mathematical limit. The absolute maximum number of groups you can form is strictly equal to the number of PSUs in your smallest stratum. Okay, once we have our groups properly divided, we have to actually calculate the variance. And this brings up a super subtle but absolutely vital statistical choice. We basically have 2 formulas we could use, V1 and V2. V1 calculates the square differences between each group's estimate and the average of the group estimates, which is theta tilde. But V2 is mathematically preferred. Why? Because V2 calculates the square differences between each group's estimate and theta hat, which is the estimate calculated from the entire complete sample all at once. Because the complete sample estimate is a lot more stable, V2 provides a much more reliable anchor for our math. Now, it generally yields a slightly larger, more conservative variance estimate, but it's the safer, better choice. Let's look at example 9.4 to see this in action, the 1987 survey of youths in custody. The researchers on this project wanted to divide their stratified survey into random groups. Look really closely at strata 2 through 5. Do you see the number of eligible PSUs in those strata? It's exactly 7. Because of that golden rule we just talked about, that your maximum number of groups is limited by the smallest stratum, the researchers were forced to divide this entire massive survey into exactly 7 random groups. No more, no less. So they created 7 workable, perfectly mirroring miniature surveys. By using a really clever facility assignment method, all the residents in a specific facility were assigned to the exact same random group. This perfectly preserved the cluster and stratum weights. And if we check out the results, the estimate of the mean age fluctuates across these 7 pseudorandom groups. It drops down to 16.06 in group 4 and jumps all the way up to 17.27 in group 7. And honestly, this is exactly what we want to see. We need this natural sampling variability to give us the data required to calculate our variance. Ultimately, when they calculated the mean age using the entire undivided dataset, the complete sample, the estimate for mean age was 16.64. By using our preferred V2 formula, which remember, anchors the variance to this stable 16.64 figure rather than just the simple average of the 7 groups, we get an incredibly robust variance estimate. Apply our t-distribution critical value with 6 degrees of freedom, and boom! The final 95% confidence interval is tightly bound between 16.3 and 17.0 years of age. Section 5. Evaluating estimation methods. Pros and cons. Excellent work navigating all that math, everyone. Now let's move into our final phase, the critical evaluation.
Because at the end of the day, as a statistician, you are the one who has to choose between linearization and random groups for your projects. Let's synthesize the mathematical and practical properties we've covered to help you make that call. First up, the calculus approach. The massive undeniable advantage of linearization is that it is the industry standard. The underlying theory is ironclad, and basically every statistical software package has this completely built in for general sampling designs. But the disadvantages are definitely significant. Remember those messy partial derivatives we wrestled with earlier? The calculations can get incredibly tangled, especially when you start adding in complex weighting. Plus, you absolutely need a large sample size for the Taylor approximation to even be accurate. And critically, and this is a big one, it is totally inapplicable to non-smooth functions.
Let's contrast that with the random group method. The biggest advantage here is that the variance is just so incredibly easy to calculate once your groups are set up. I mean, it's literally just standard deviations. And because no derivatives are required at all, it easily handles non-parametric problems, percentiles, and those tricky non-smooth functions. However, the disadvantages are very real. Setting up the random groups can be an absolute logistical nightmare in complex designs. You have to be so careful to ensure every single miniature survey mirrors the complete design perfectly. And if your survey design limits you to a really small number of groups, say under 10, like in our youth custody example, you end up suffering from huge t-critical values. This artificially inflates your confidence intervals, leading to imprecise variance.
So I'm going to leave you with this final thought to really test what we've learned today. Which variance estimation method would you choose if your survey's target parameter was a non-smooth function, like a median? Well, if you said random groups, you hit the nail on the head. You absolutely cannot take the derivative of a median, so linearization is totally off the table. I really hope you leave this explainer super eager to apply these powerful theorems to your own complex survey data. Keep practicing those proofs, keep questioning your data structures, and I will see you on the next explainer.